Okay, so in this particular video, we have a car that accelerates uniformly from rest and it reaches a velocity v after 1 second. Okay, and the problem wants us to find A, B, C, and D. So here in the diagram, I have the car starting at rest at times equal to 0. Its initial position is 0 meters to start. And it says here in the diagram that after 1 second, it reaches some velocity v, okay, at exactly 1 second. So as it picks up speed, if you were to momentarily clock the car, it is moving at a speed v, which I don't know what it is because it doesn't matter what v is. These types of questions are designed to ask you to express the answer in terms of the variable given. All right, so let's knock out A, B, C on the slide, and then I'll do D on the next one. All right, so let's do it. It says here in part A, find the velocity at t equals to 1.5 seconds. So essentially it's saying find the final velocity at 1.5 second, except express your answer in terms of v. So here it doesn't really care for what the number is, it just wants you to express it in terms of the given variable again. All right, so let's knock out part A. So in order to do part A, you have to recognize what's given. So here I have Vf is equal to At plus Vi. This is a kinematics equation that you should know hopefully by now in this point in your kinematics physics career. Vi is equal to 0 for this particular problem because it sets uniformly accelerate from rest, which implies that Vi is equal to 0. So pay attention to initial condition given as you practice. Here, Vi is 0 because it said so. So really the function for Vf reduces down to just At. But you notice here, instead of Vf, I call it V because the initial given condition says that the final velocity after 1 second is just called V. So instead of calling it Vf, I'll just call it V, which is what the diagram has, okay? Again, Vi is crossed out, so really you're left with just A and T. So the final velocity equals At. I don't know what A is, and I don't care what A is because it says uniformly accelerated. Pick whatever value A if you want, but it doesn't matter. That's not the point of this. The point is that whatever A is, it just stays A throughout the whole entire problem. So what does matter is the time that it, ticks. All right. So let's do part A. So this is our reference point, and it's important that you understand baseline or reference point. In order to do part A, we should set up the time interval from 0 to 1.5 seconds because part A asks to find the velocity at 1.5 seconds. Here I've chosen to go from 0 to 1.5 because I think it's the easiest one to do to find the velocity at 1.5 seconds. But if I start at 1.5 seconds, if I start at 0, I know my Vi is 0, and then I want to go all the way to 1.5 seconds. So what is this velocity here in terms of V, the velocity at 1 second? So to do so, we can just set up the kinematics equation again, same function, Vf is equal to At plus Vi. But I do want to point out that this Vf here is the final velocity at 1.5 seconds. So if you're not paying attention carefully, you might think these final velocities are the same. The answer is no. These final velocity occurs at the final time that's given in the interval. In this particular problem, part A, the interval is from 0 to 1.5 seconds. So the final velocity here occurs at 1.5 seconds. Okay. If I start from 0 second, my Vi is going to be 0, so I'll cross that out. So my final velocity is just A, whatever A is. Here, I have substituted T for 1.5 T. Again, I do want to point out that these functions that I start with, these are what I reference as generic equation. These equations allow you to solve for final velocity, but you just have to know how to apply it carefully. So final velocity is equal to acceleration times time. But what is this time? This time is 1.5 t. It's 1.5 t because the diagram and the statement tells us information for just the first second. It says after 1 second, the car attains the speed of v. Well, I don't know what v is, but I know v occurs at 1 second. So therefore, 1.5 second is just 1.5 times 1, which is whatever t is, which is our baseline or reference point. So it's important for you to understand where the 1.5 t comes from, okay? So 1.5 t is simply 1.5 times 1. Why 1? Because t given in the reference point occurs at 1 second. All right. So therefore, I can just go ahead and move the coefficient 1.5 out in the front. It leaves me with 1.5 AT. But I want to box AT according to our reference or our baseline. AT is just V. What V? V at 1 second. Okay. Therefore, because I know what AT is equal to, I can substitute in AT for V. So my final velocity is 1.5 times V, whatever V is. So if V here is 1, my velocity over at 1.5 seconds would be 1.5. If the velocity here, let's say, is 8, well, my velocity here would be 12 because it would be 1.5 times 8. So the ratio will stay the same, except the value varies because I don't know what V is, okay? Because I don't know what A is. Because I don't know what A is, V final can be any values. It can be infinite. All right. So therefore, my final velocity here is just 1.5 times V, whatever V is, which I don't know and I don't care. All right. So therefore, the final velocity here after 1.5 seconds is just 1.5 times V. Which V? Whatever this V is to start with the problem with, the baseline, the reference point. All right, let's do part B. Part B asks us to find the velocity at 2 seconds and express it in terms of V. So we're going to use the same process. So here my arrow is a little longer because I know that it's accelerating, aka it's going to be speeding up, so the velocity technically is going to get a little faster and faster. So my arrow is a little longer here. And this is going to start at 0 second and it's going to go to 2. Well, if it's going to go from 0 to 2, here at the top, here's my time. I want to find the final velocity at exactly 2 seconds. I don't want the average. I just want the instantaneous, okay? So the V at 2 seconds is your instantaneous velocity, which in physics is your final velocity at that time. So here generically I have VF, which is my final velocity at that moment in time, times A times T plus VI. But I want to start from 0 second and I want to go to 2. And if I start at 0 second, my initial velocity is 0 according to the diagram and according to the statement it says start from rest. So I'm just going to go ahead and cross again VI out. I want to put A. I want to carry A down because I don't know the value for A. But here in the generic equation it's just T, but I've gone ahead and substitute T for 2T. Well, why is it 2T? Because part B asks you the velocity at 2 seconds. 2 seconds is 2 times the initial amount, which is 1 second. So our reference point here in this particular problem is at 1 second. Okay, so it's important. These reference point can change, but here I kept it at 1 second just so it's easier to do. Therefore, because T is 2T, I can pull out the 2 in front, and then I'm going to keep the A as my next variable, and then T is my last. But as I did with the first part in part A, I want to recognize that A times T is my reference point. A times T is whatever V is. So therefore, wherever AT is, I can substitute in for V. So I want to write the same VF. My final velocity is 2 times V, whatever the value for V is again. So the point of these ratio problems is not for you to actually calculate a number. It's for you to express answer in terms of variables, okay? All right, therefore, the velocity at 2 seconds is 2V, whatever this is. So if V is 2, this is 4. If V is 6, this is 12. If V is 20, this is 40, and so on and so on. As you can see, the answer is infinite because I don't know what the acceleration is, okay? All right, let's do the last part of this type of question, part C. Part C asks us to find the velocity at 3.7 seconds in terms of V. So we're gonna follow the same procedure, okay? So here's the car at 3.7 seconds down the road somewhere. And then my velocity here is going to be a little bigger because it's accelerating. In this case, it's going to get faster and faster. So my velocity vector is going to get a little longer and longer. So I'm going to go from 0 to 3.7. I'm going to follow the same strategy I've been doing the last 2 parts. I'm going to cross out VI because I'm starting at 0 second. I want to put in A. I don't know what A is. I'm just going to carry that variable down. Here, T is just 3.7 T because, again, it wants us to find the velocity at 3.7 seconds. Our reference point for this particular problem occurs at 1 second. So it's important for you to understand that, okay? Your reference point for this problem is at T is equal to 1 second, which makes things easy. It doesn't have to be 1 second though. Therefore, we can rearrange this, pull out the coefficient, which is 3.7 out in the front. write the A next to it, write the T next to it. This is, I think doing this is easier to allow you to substitute quickly. And hopefully by now you recognize that A times T, all the way back on the left side of the screen, A times T is V. So instead of writing AT, we can just write V because that's a true statement. So therefore VF here is 3.7 V. And that's our answer, okay? So at 3.7 seconds, how fast is it moving? It's moving at a rate of 3.7 V, whatever V is. All right, here's the thinking part. If you haven't caught on yet, the ratio here, the final velocity is always going to be the multiplier of whatever time is. Here's why. Well, here generically, I have VF is equal to AT, but instead of VF, I just wrote V because the diagram just calls it V. It can call it VF if it wants. It can call it V of T. It doesn't really matter to me. Okay, hopefully it doesn't matter to you. So whatever V is equal to AT. Well, again, there's no VI because for this problem, VI starts at 0. But what I notice here, though, is that whatever A is, I don't really care. Why? Because A is the same throughout the whole problem. So you notice here, my A keeps coming on and off the screen. I don't care for what A is. Okay, you can pick any number for A you want, and the answer will still be the same. I don't care what A is because A is just a constant. Because A is a constant, I'm going to go ahead and take that out of my equation. Why? Because it doesn't really matter for a ratio problem. So instead of saying V is equal to AT, I'm going to take A out because it doesn't matter. Therefore, I can rewrite the statement. V is proportional to T. You notice that the equal sign changed to a proportional sign. Now, why is that important? Because I know that if T goes up by whatever amount, because it is proportional to, V on the left side has to go up by the same amount for that statement to be true. Okay, so in physics and in math, we call this a direct proportional or direct proportionality. All right, so in this case, we say V is directly proportional to T. So if T goes up by 4, V goes up by 4. If time goes up by 10, V also goes up by 10 in order for the statement to be true. Listen to that again. Let it soak in your brain. All right, here in part D. Part D asks us to find the ratio between the change in velocity between 1.5 to 2.8 seconds compared to the change in velocity between 2 to 4.5 seconds. Well, easy to do. In order to find the ratio, we need to figure out what our delta V function is. The average acceleration function is equal to delta V over delta T. Here we want to isolate for delta V because the ratio has to do with delta V. Okay, so I'm going to keep delta V condensed the way it is in the function. I'm going to get it by itself. In order to get it by itself, we must multiply both sides by delta T in order to get rid of this denominator delta T. So here in my work, I'm going to have on the right side multiply by delta T, on the left side multiply by delta T. And we'll clean it up a little bit here. So therefore delta V is simply A times change in time. Well, I don't know what my A is, but I do know what my change in time is though. So here for part A, I'm just going to do it twice. I don't know what A is, so I just carry the A's down. Here next to it, I'm going to multiply by 1.3 seconds. Now the 1.3 seconds comes from this right here up at the top. Okay, the interval is 1.5 to 2.8 seconds, so therefore the change in time in this first interval is 1.3. 2.8 minus 1.5 is 1.3. So that's where the 1.3 second comes from. On the right side of my statement here, I have A times 2.5 seconds. Well, why is it 2.5? Because the second interval of time given in this expression is from 2 to 4.5 seconds. So 4.5 minus 2 is 2.5. So that's where that 2.5 second comes from. So what I want to do is I'm just going to rewrite the statement from the top in part D. Part D says blank delta V from 1.5 to 2.8 is equal to delta V from 2 to 4.5 seconds. So I just carry that same statement down here. Therefore, we can substitute in delta V between 1.5 to 2.8 seconds, which we already calculated here. Watch what I'm circling. So this delta V here is the first statement on the left. The 1.3 comes from taking the difference between 1.5 to 2.8 seconds. So we can say delta V is just A times 1.3 seconds, which is what I've written here on the left side. On the right side, delta V for 2 to 4.5 seconds. So delta V here is A times 2.5 seconds. Again, in case you missed it, 2.5 second came from taking 4.5 seconds, and we subtract that from 2, which is 2.5 seconds. So therefore, delta V is A times 2.5 seconds. So I just substitute that statement in, and here's my heart to fill up the blank. And to solve for heart, I divide both sides by A times 1.3 seconds. And then A is going to cancel out, and then the second unit is going to cancel out. So therefore, 2.5 divided by 1.3 will give us a value of about 1.92. So therefore, this is your answer. So your coefficient is 1.92. Again, it has no unit because everything in terms of units cancels out. It has no direction because it's just a number that expresses a true statement. This coefficient has no unit, and it doesn't have no direction. All right. Other than that, I hope that helps. Stay nerdy. Don't be whack.